All right, let's get going. Okay, so I want to say a couple things about Canvas. So I feel like this was the first time I've ever used Canvas for homework. I feel like it went okay. I didn't get any major problems, major complaints. You'll have a chance to give your feedback at the break. We'll do a quick polls everywhere about Canvas. Not a fun word cloud, an actual poll. But two things about it that I did notice is if you're trying to do the geyser problem, there was geyser 1 and geyser 2. So geyser 1 accidentally got set with a tolerance of 110%. Okay? So any positive number you put in was going to be correct. Geyser 2 needed that number and didn't have that tolerance, right? So if you got geyser 1, that was easy, and you can't get geyser 2 to save your life, it's because you have the wrong number from problem 1. Okay, so I fixed it for a lot of you. I don't know how to regrade a problem yet. I don't think Canvas can do that. So if you got geyser 1 on a freebie, good for you, but that might be your problem with geyser 2. All right? That's like the last two problems, I think, or near the end. So that went wrong, but that was a minor setting problem. And then this system is not meant for homework where it's open and you help each other. It's meant for a test where you take it and you never talk about it again. So I think on the numerical response with 10 chances, most of you are either giving up or getting it after 10 chances. But on the multiple choice, it's very reasonable to use up all your chances and not get it. That's okay. That can happen. You only get 2 chances. So you miss it once, you miss it twice, and then it disappears. And that's a setting I can't change. So if you miss a multiple choice twice, you won't be able to even see the problem again until the thing is due. Okay, that's just a weird Canvas thing that I can't fix. Okay, so if you miss multiple choice and you're just desperate to see it again, just email me and I'll send you a screen capture of it or something. Okay, but it's normal if a problem disappears. You'll see it again once it's due, I think. I mean, that hasn't happened yet. But the first homework is due Wednesday midnight, so hopefully all the ones that you used up all your tries on will become visible because we want to be able to use them to study, of course. And then someone also asked, can we ask you questions about Canvas? And the answer is yes. So Canvas is not pledged. It's just a homework. We want you to try to do it by yourself, but you can talk to each other. You can talk to us about it. It's just like any other homework problem. Okay? So that is Canvas. And we're interested in feedback to see how it's going. Yeah, you can't beat the price. So what do Taylor Swift and last week's material have in common? Does anybody think they might know what they have in common? Oh, they're both one-dimensional. Oh, sick burn. So last week we talked about one-dimensional kinematics, right? So hopefully from last week you learned all these topics. Unit conversions was sort of for fun, that fun problem y'all did, which some people didn't find so fun. But we went through and talked about the concepts in calculus and kinematics. We derived, it's really just 2 equations. It's really just VF equals V naught plus AT, and XF equals XI plus VIT plus 1F AT squared. That's really all of 1D kinematics, those 2 equations. If you have constant uniform motion, you set the acceleration to 0. Okay? And then we took those 2 and made a third one. So hopefully you got a little experience at where those came from, how they're related to calculus, how they're related to each other, and how to plug them in and do problems. And of course, analyzing graphs will be important. So hopefully you got a little experience with that. And then we showed you some of the trickier problems. We didn't quite get to them. I made videos of them. Hopefully you found them and helped you do the homework, right? And then there's always this. We can always come up with something out of the blue. Yes, 5% of the exam might be out of the blue. Okay, so hopefully that all made sense. So here we go this week. So this week, we're taking it to 2 dimensions. Oh, no, what happened to my system? Oh, it's just on the thing, funny. It's all new. Let's see, here we go. So this week we're going to talk a lot about vectors. I'm going to spend a whole half lecture on vectors. So if you're uncomfortable with vectors, you'll be more informed about why you're uncomfortable at the end of this first half of the lecture. So we're going to talk all about vectors, how to draw them, what they're all about, how to add them, subtract them, multiply them by a constant, and how to identify them. Notice we're real big on looking at graphs and understanding things graphically. Right? That's going to continue to be important with vectors. Then the most famous 2D problem is projectiles. We'll spend some time on projectiles. And then we'll do, Thursday, we'll do moving reference frames, and we'll just do a bunch of practice problems on Thursday. Okay, so 2D kinematics is what we're moving on to today. Okay, so let me get the lights on here. Did that just happen? Or no. Okay. So vectors. Let's see. All right, so vectors, here we go. Vectors are numbers with Metadata would be your generation's way to think of vectors. It's a number with just a little bit more information attached to it, right? And we always identify them by contrasting them to scalars. These are the numbers from your youth. Before you had to think about vectors, you had scalars. You had your age, right? Your SAT score was a scalar. Your mass is a scalar. Your phone number is a scalar, etc. So those are just simple numbers. Another way to think of them is quantities. Except your phone number, those are all quantities. Then, of course, vectors are the ones that have the famous definition, which is a quantity with a direction. Quantity with a direction associated with it. So we've already talked about them, right? So velocity is a scalar, and acceleration are the ones we've talked about, and displacement, it's a vector, and displacement were all vectors. And you can think of more, right? So force that we're going to talk about next week is a vector. There's others. I don't know. Let's see. Let's see. Okay, so let's talk about how to draw vectors. Okay, so this is vector anatomy, and this is actually important. You can mess this up. Okay, so if you're going to draw a vector, it's an arrow. That's all it is. You draw the arrowhead on it. You can draw the feathers on it if you want. I don't recommend it. It'll make your drawings more confusing, right? So it's just an arrow, and the symbol for a vector is you put a hat on it. Symbol has an arrow hat. Right? Like that. So you'll see me writing all the time, putting those on there. That's a little vector above the V to tell you that it's a vector. Or in a book, or bold. Right? In a book, you might see, oh, it's bold. Like it's hard to do on the chalkboard, right? Books often just make a number bold to make it indicate it's a vector. But on a board, we give it a hat. Okay? Now, the vector is an arrow, and of course, it points in the direction of the vector. Its length is the size of the vector. We'll get more into that mathematically in a minute. But one other thing I want you to know is into the board and out of the board. So we need a way to do a little bit of 3D later. We're not really going to get into this now, but before the semester is over, we'll need to have vectors going in and coming out. And the way you do that is you think of it as an arrow. It is an arrow, right? So if an arrow is coming at you, it's going to hit you right in the face. What do you see? That's coming out of the board. Here comes the arrow. So it looks like this. It's like the point. Right? That's the point of the arrow headed to your face. That's a vector coming out of the board. We won't do it this week, but it'll come eventually. A vector into the board. After you shoot the arrow, what do you see? You see the feathers, right? It's a little X. Those are the feathers going away from you into the board. Okay? So that all sounds not so hard, identifying vectors and directions. But there's one way to make it tricky already. And that is, we're going to eventually talk about tension in a string. So if you took a little physics, you might know that tension is something. Is tension a scalar or a vector? I'll do a 1, 2, 3. And you say scalar or vector. Tension is a 1, 2, 3. Well, that's pretty good. A lot of you did say scalar. It's a scalar. What? Why is it a scalar? So think about it. I meant to bring like a string with something hanging on it. So tension is a scalar. It's a scalar property of a string. And the string applies a force at anything attached to it on the ends. Right? So there's tension and the tension force. Those are actually different. We often just say tension. And we draw T. And we put a vector on it. That means we mean the tension force. T is the tension. And it kind of makes sense if you think about it. If I just have a string under tension, which way is the force? It's this way or this way. It depends on what it's attached to. It only applies the force at the end. Right? So then it applies the tension force here. And if there's another wall here, it applies the tension force there, pulling in. Okay? But the tension itself is a property, a scalar property of the string. So your homework has one other tricky one like that. Here's your hint. There's another famous common one that you think of maybe as a vector, but it's really a scalar. Okay? So it's not quite as straightforward as you might think it is. Okay? Okay, so now let's see. We've got to next describe 2D vectors a few different ways. So describe 2D vectors. And here's the whole reason vectors are hard. We're going to describe them mathematically, is that you jump between two coordinate systems. You may not have had it called this before, but that is the reason. In two coordinate systems. So we're working in 2D here, and we have two coordinate systems to think about. Okay? And often you'll do one part of a problem in one, and you'll have to switch and do the other part of the problem in the other, and they'll ask for the answer back in the first one, and you got to go back and forth. So I like to give them friendly names. So the first one is called polar bear coordinates. This will help. This will make it seem not so bad. Okay? So let's describe the vector 5 meters per second at 25 degrees. Say a problem gives you that. The velocity is 5 meters per second at 25 degrees. So there is an origin to the polar bear coordinate system, and you can draw this velocity vector at the origin, and we'll talk more about where to draw vectors. It's kind of confusing. It seems like you can draw them anywhere, and it depends. You can. But for now, we'll just say here is 5 meters per second, and here is the origin, and it's a mass moving, so it's not just the origin. We'll say that's the mass moving like that, and I always draw a little polar bear, my polar bear coordinate system like that. I practiced that all summer. We're drawing those for you. So this is the vector. We said, oh, if it's a velocity vector, it must have a v like that. Okay. And then what you do in a polar coordinate system is you draw a horizontal axis through the origin, or through the location of the object, which we're making the origin here, and you define the angle theta there. Okay. So let's look at some properties of this. So let's see. There's basically, it takes two numbers to describe that vector. It takes the size, the magnitude, and the direction. So this is how we define them in this coordinate system, is you put in magnitude bars, or absolute value bars, on the vector. Right? The vector itself, with a vector head on it, indicates both pieces of information, the magnitude and the angle. So now we're going to show you mathematically how you take that apart. You need the magnitude, and this is the magnitude. It's also just the length. It's also just the quantity, right? That's all it is. Not the direction, everything but the direction. Magnitude, length, quantity. And the main thing is it's always positive. The magnitude cannot be negative. Right? Something can't have a negative length, right? It's always a positive length. Okay? So you might see it like this, or you might see somebody put the bars like this and say, well, there's the magnitude and there's the direction. Or you could leave the bars off. The key is to know that the magnitude is just the length. Okay? And then theta is the angle counterclockwise from the right horizontal axis. And those are all important to keep up with if you're going to do this mathematically. Or you can do it by intuition. Both are allowed. All right. Somebody's pointing out that it's cold in here. I have heard that before. Let's see. So this is important. So we can talk about angles, and in problems there'll be angles all over the place. But if you want to follow strict mathematical convention, and sometimes you do and sometimes you don't, and I'll show you when you do and when you don't, this angle is 0 and positive is that way. Okay? If you want to be very strict and formal about where the origin of theta is, that's where it is. Take wherever your coordinate system is, draw a line to the right, that's 0, and positive goes counterclockwise, not clockwise. Okay? Okay, so that's polar bear right there. That's it. So now let's look at the other one. The other one is, and also one thing to point out, we're going to compare them. So this is a two-dimensional coordinate system. How many numbers does it take to describe a vector? 2, right? Two-dimensional coordinate system takes 2 numbers. So let's look at the other one, the Cartesian coordinate system. So does anybody know who the Cartesian coordinate system is named for? Rene Descartes, right. So I call it Rene Descartes Cartesian coordinates. Okay? Rene Descartes would have been, invented all kinds of stuff in science. Would have been the greatest scientist ever. If I showed you the slide, he comes after Galileo and before Newton. But he became obsessed with philosophy. Oh, so close. He was figuring out how the universe works, and he thought, wait a minute, how do I really know that? My senses are fallible, so maybe when I turn the light switch on, that's not why the lights go on. And then the rest, then he just wasted his life, but whatever. He could have really made a difference. Okay. So let's say our example is 4 meters per second I hat plus 3 meters per second j hat is how you write it. Okay, so those unit vectors, hope that wasn't a philosophy major, those unit vectors really give people hives, so we're going to talk about it. Okay, so what you do is you draw a vertical and a horizontal. So this is the plain old coordinates that you're used to, Cartesian coordinates. By tradition, you make this plus x. By tradition, you make this plus y. I usually mean that the origin is there if I don't say anything. All right, so it's just an x, y system that you're used to that makes a lot of sense. And you describe it, we'll call it v again. Let's pretend this is it is a velocity vector, with, not magnitudes, components. So that is a word that we want to contrast to magnitudes, and we'll call it Vx and Vy. Okay, let's contrast for a minute. Here we care about magnitude and angle. It took 2 numbers. This is always a positive number. It's a length, and this is an angle. Here, it's going to take 2 numbers, 2 components. Here they are, Vx and Vy. But they're not magnitudes. They are components. They can be negative. Okay, can be negative. So let's draw them. So what that means is these are scalars. So we say Vx is a scalar, and we just measure out to where Vx is. Vx is this one. So we measure out 4. There we go, 4 in this case. And then this one is Vy, the one that we call j hat, whatever that means. We'll get to that in a minute. So then we go up 3. 3. Okay. So the vector is sort of at the intersection. If you want to draw yourself a couple of dotted lines there like that, there it is. So there's V right there. Okay. So again, it takes 2 numbers, just like it takes 2 numbers over here. Any vector could be described in either one. Oh my God, I forgot to draw Rene Descartes like this. Got the goatee action, the crazy hair like that. There we go. Okay, so now here's how we write it. I don't write in like logical order. Sorry. Okay, so then I accidentally gave it away over here. We'd write it. No, I'm doing it with symbols now. So you put whatever Vx is, I hat, plus whatever Vy is, j hat. So all that means is Vx along the x-axis, Vy along the y-axis, and make the vector go to the corner of that rectangle. Okay. So Vx and Vy are components. They can be negative. And then I hat and j hat are unit vectors. So that's a concept you need in a Cartesian coordinate system. I'm not supposed to tell you this because you're bioscience people and you'll freak out. Okay, but I'm going to take a chance and tell you this. There are unit vectors in this coordinate system. Okay, there is a theta hat. Okay, it's okay. There's a theta hat. Just in case you become mathematicians, I want you to know that. Okay. So I and j are unit vectors. They give a direction, but they don't affect the magnitude of the vector. And the reason is each one of them has a magnitude of 1. That's why it's called a unit vector, right? So you're saying Vx along the x-axis, and this is just 1, so a distance Vx along the x-axis, like this, plus a distance Vy along the y-axis, like that, and then that's the answer. Okay? You're really just adding. It's vector addition. When we do vector addition in a minute, you'll see how it all works. Okay? Unit vector is also the funniest of all the vectors because they have a caret top on there. That's a caret on the top of the thing. Okay. I met him this summer, so I thought it was relevant. Okay, so let's see. Yes, okay, so this seems fun. This seems great. How can we possibly make this hard? Let me show you. Let me show you how we can make this confusing. So this is tricky because problems, so physics problems, typically give you polar coordinates. You know, the boat is moving along the 45 degrees north of west or whatever, and that's how you find out. Oh, God. I don't know why this isn't ringing. I don't understand. I'm sorry. Oh, Lord. Let's see. Okay, some of these we'll talk about later. Rest your hand for a minute. What are the symbols besides meters per second? Okay, we did that now. That's I hat and J hat, right? Yeah. Will problems on the practice test deal with angles in degrees or radians? Good question. We're going to start out in degrees. We may get to radians eventually. Okay. What are the curvy unit vector arrows are? Yeah, so So those are the unit vectors. Well, yeah. That little hat, this thing is a little, it's a caret. It's an upside down V, that little thing on top. Okay, so problems give you polar, but to do the physics, you need Cartesian. And to do physics is sort of a loose freshman physics, what I mean, to do the kind of problems we're going to do, okay? So for example, what we're going to do is we're going to learn to go back and forth, okay? So say you're given a problem. So problems give you polar. So let's look at a problem where we're given polar. Let's say we have a vector that looks like this. Again, looks basically the same. We have a velocity vector like that. And we're told how long it is. So there's the magnitude, my little V with a bar around it. And we're told the angle, theta, right? So that's what you get in a problem. We want to convert to Cartesian. So what you do is draw yourself a Cartesian coordinate system right on top of it like that. There's X and there's Y, right? And then you use SOHCAHTOA, right? So hopefully, did you all hear about SOHCAHTOA? How many have ever heard the word SOHCAHTOA? Yay. I don't know what story they tell you now. Probably not the one that I learned in the 80s. Unlikely. So its sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent, right? It's just a way to remember all these little relationships. And that's true for a right triangle, right? So what you do is you say, I know my two components look like this. There's the Vx I hat component. There's the Vy j hat component. And now we're going to move it over like that. There's the Vy component there. This is the Vx component here. So all I did was slide it over to make a right triangle, right? So then I don't care which one to do, but let's do cosine first. Cosine theta is adjacent over hypotenuse. Adjacent is Vx. And now here's your first test of your ability to do mathematical numbers. Don't put V in the bars. The magnitude of V. Get some practice writing the right thing. You don't want to put a vector in the denominator of a fraction and think it's going to make sense, right? Cosine theta is a scalar. This is a scalar, and this is a scalar. So a scalar divided by a scalar makes a scalar. The scalar divided by a vector, if you left those off, I don't know what that is. That's confusing, okay? So write it correctly, and then you can easily solve for this component. Vx equals the magnitude of V times the cosine of theta, right? And then you're familiar with sine of theta, Vy over V. Sine is opposite over hypotenuse, so Vy equals the magnitude times the sine of theta. Right? So that's how we can get, so if you're given, polar coordinates, you have the angle and you have the magnitude. And this is how you take the angle and magnitude and you get the Cartesian coordinates from those two. Right? You've probably seen that in some trigonometry class or something like that. Right? So you say, oh, how could they make that hard? Oh, okay, well, let's see if we can make it hard. So you might be given a problem, and they might say, look, the velocity is this way. Right? And then what are you going to do? This is like, we're going to find out, who you really are here. You're going to say, well, let me draw a Cartesian coordinate system like this. Okay. He said to put it at the origin, and then what did he say? I don't know. Nobody's listening. Then you put an angle on there, and you can say, well, I guess I'll put the angle here. And you can. if you know what you're doing, right? So you say, okay, well, this was the magnitude of V. That's fine. Here, sorry, that's ugly, right? And you say, okay, I need the two components. Well, I need this component. That looks like the y component. And I need this component. And if you apply SOHCAHTOA, you'll get pretty close, right? So we say, well, sine is opposite over hypotenuse. So we say, oh, the Vx is the magnitude I was given times the sine of theta in this case. But that doesn't match the standard version, right? It doesn't match because you define angles from the x-axis, not from the y-axis. You can define it from the y-axis, but then you've got to use SOHCAHTOA to get your own formula here. Okay? And you also have to watch your negative signs if you make up your own theta version. Because is this positive or negative? Well, it's negative, right? If you plugged in the numbers, you might get, oh, it's 3 meters per second. And the way you're going to get it is you're going to go, oh, it's to the left. Right? 99% of us do our negative sign that way. I did a triangle. I know this side of the triangle is 3 meters per second. And I know it's to the left because it's pointing to the left. So I put a negative sign. That's okay. You can do it that way. That's how most people do it. Now, when you get into really complicated problems with like 20 angles, you might start to get messed up. But for most of what we're going to do in this class, you can just do that. But if you're a rule, how many rule followers do we have here? See, I'm not raising my hand. Okay, that's good. It's good to be a rule follower. If you're a rule follower, you say, well, this is what they gave me. I want to say this angle. I'm going to add 90 to it. And then you can go straight with these formulas that let you sleep better at night, right? So if this was 30 degrees and the sine of 30 degrees is, I'm going to say a half. I forget which one it is. Say it's a half. You know it's a negative half. If you say, oh, no, I'm going to do 120. I'm going to do 90 plus 30 is 120, and I'm going to follow this standard formula. You'll get negative a half. Right? So going the standard definition, in addition to getting the angle right, will also give you the negative sign. You won't have to put it in artificially. Okay? So just watch. Problems don't always give you the angle counterclockwise from here. They'll give you the angle other ways. Okay? Let's see. And then, of course, the y component, you'd have to say, okay, well, I use SOHCAHTOA to get Vy. Cosine theta, because y is adjacent over hypotenuse, and you'd have to use your knowledge to say that one's positive. I'll get some positive number here, and it's positive. That's how you'll know. All right. Let's see. Is Vx a vector component? Does that make it equal to the magnitude? Oh my God, no. So let's do it again. Components are not the same as magnitude. So magnitude is the idea that applies in polar coordinates, and it is the length of the vector. It is literally, get a ruler out. How long is the vector? It can't be negative long. Does your ruler have a negative side on it? No. You can measure displacement negative, but you're not going to measure a length with a ruler that's negative. So the magnitude is always positive. The component can be negative, because it's just a scalar that describes an axis. Okay? So let's think about this for a second. If we wanted this vector to go the other way, let's describe this vector now. How would we describe this vector? It'd be like the same magnitude, but we'd add 180 degrees to the angle. Right, so if you want to make this negative, you change the angle, but this can't be negative. If you want to make this negative, and you want it to go the other way, you put a negative sign on the two components, because they can be negative. Okay, so there's a very big difference between those two things. And it's very easy to mix up. That's why I'm like making a big deal about it. It's very normal that you would mix that up. Okay. All right. So that is how to go. That's only one way, right? That's how you have polar and you need Cartesian. Then you do all the physics in Cartesian, and then the stupid problem. Yeah, go ahead. Yes. Yeah, you can do it any way you want. You can define theta from any way you want. If you do your own if you do your own SOHCAHTOA triangle, you can do anything you want and get the negative signs right. You could even say, this isn't 90 plus 30. This is negative 180 plus 60. And then use these formulas if you want. Right, yeah. So yeah, you can do it any way you want. Just, you got to get the negatives right. So now we've got to go the other way. So we do all that. We get it in Cartesian. We do the physics. We get the answer. And then the stupid problem says, give the answer in polar coordinates. Right? So now we've got to go back. Right? So let's see. So the answer in polar coordinates. So this is the case where we have the vector answer now, right? And we know it's x component, and we know its y component like that. We know those two numbers, so we got to go the other way. We got to go the other way. All right. I meant to, let's here. Sorry. Let's do it down here. Let's make it more exciting. There's Vx and there's Vy. Right? I did not make the symbol negative. Vy is a variable. It can be positive or negative. Okay, so I just wrote Vy down there. I didn't write it negative. Okay, so we have Vx and Vy. We want, what do we want? We want, damn it, we want those two things that were there. We want the magnitude and the angle. So the magnitude you get from the Pythagorean theorem, right? So this makes a triangle, Vx, Vy, right triangle. The square root of this squared plus this squared is that. So it's just the square root of Vx squared plus Vy squared. Like that. Is there any way you can get a negative number from this? Okay, well there is, but no, there's not. There's not. Okay, yeah. Y, these are components. Vx squared plus, oh yeah, oh my God. What? Yeah. This is Vx, and then I'm sliding over, and this is Vy. Thank you. There you go. Yeah. So it'll always come out positive, just because the magnitude always has to be positive. If you put two real numbers in there and you square them, they've got to be positive. You take the square root, it has to be positive, so it'll be positive. And then you get the angle, you go back to your SOHCAHTOA, the last part, right? Theta is the inverse tangent, and that freaks people out, but it's really not that bad, of the y component over the x component, right? So here's your right triangle, there's your angle. The tangent of that angle is opposite over adjacent, Vy over Vx. So we just take the inverse tangent and you get that, okay? And if you had numbers like this, if you plugged in a positive Vx and a negative Vy, you'd get a negative number, and the inverse tangent of that negative number would be a small negative angle, because we're following the mathematical convention here. It'd be a small negative angle relative to the horizontal axis. But this formula also depends on how you set it up. You know, you could come over here and say, I have this Vx and Vy. What's the angle if I do the formula for this right triangle, and you do an inverse tangent, you'll get this angle. But if the book says, what's the angle relative to the horizontal, you got to add 90 to it. So you just got to, you can use SOHCAHTOA all you want, but just think carefully about what you're being asked sometimes. And there's nothing tricky like that on purpose, but that's just how it works out. Let's see. How can you use SOHCAHTOA for the larger angle if it's not right triangle? Then you flip it over and you do the right triangle the other way. Okay, so SOHCAHTOA is only for a simple right triangle. Right, so somebody's asking basically, here's a right triangle. What if the angle is here? I mean, I can't make a right triangle anymore. Well, now this is your right triangle. So you can always make a right triangle between a vector and two perpendicular axes. It's always possible. It just may not be where you want it to be. Mm-hmm.
So in the example that we just did, where did the I hat and J hat come in? Or are those not valid?
The example we just did, so here we go. Here, if I wanted to formally write this out, I would have said V is Vx I hat plus Vy j hat. I never actually said that, but that's how you write it out. When we use I hat and j hat or something, it's one of those, you just got to use it. When you use it, you'll get used to what it means. I'm going to try to explain, but until you use it, it's just, what the hell's that, you know? How did you get the formula for answering in polar? These two, so this is the Pythagorean theorem for a right triangle, right? And this is the fact that tangent is opposite over adjacent for a right triangle. Those are just properties of right triangles. Took me straight to those. So we're not going to go re-figure all that out. All right. Oh, now we got to do vector math. Let's see. And then we'll be done. Oh my God. Let's see. 2D motion, yeah. Now let's save vector math. We'll do 5 minutes, early break, 5 minutes. And then we'll do the adding these things. Okay, let's keep going because I spent a whole half a class on vectors and we didn't even finish. 31%, it's a pleasure. Wow, I'd like to Christmas shop for you guys. You guys are easy to please. 31%, really love homework Canvas. Okay, so there's a lot of time on vectors, I know, but if there's one mathematical thing you're going to use all year, it's vectors. So it's worth it. So we're just going to do it. We're going to keep going. Now let's look at vector math. So the problems I was going to do, I'll post or something. Okay? So one way to do vector math is basically say a scalar c times vector a. So mathematically it's not that big of a deal, but I think it'll help reinforce what all these terms mean if we go through it. Okay? So remember, you're going to draw a lot. I promised you at the beginning you're going to draw like balls and tracks and all this stuff. You're also going to be tagging your drawing with vectors all the time. You got to get good at drawing vectors. So we did the anatomy of the vector, right? So you can do that. Now let's look at a diagram of how we would multiply two vectors. Let's say that you're just sort of drawing them like this, and you say, oh, here's vector A. Okay. And now it says to multiply it by C. Well, what does that look like? Well, it depends on what C is. All right. So if, say, C equals 2, it'll look kind of like this. It just makes it twice as long. Right? It's just multiplying the length. Right? What if C is negative 0.5? What would it look like? Well, it affects the length, and then the negative sign makes it go the other way. So it would kind of look like this. Half the length in the opposite direction. So there's CA, like that. So that's just graphically, visually, what the constant would do to it. Okay? Before we tear it too far here, I forgot some of these about unit vectors. Yes, unit vectors are confusing, I know. There's confusion about the lab times. We'll be posting something after class about the mix-up about lab times. So you'll just watch your Canvas notifications. You'll get an email. It says diagrammatically, when you're drawing, this is what you would do. If you're going to multiply it by 2, you just make it twice as long. Let's look in polar. What if we have to do it mathematically, though? What if we do it mathematically? Well, in polar, really polar and drawing are kind of the same thing. We don't do unit vectors in polar. It's really just thinking about how you would draw it. So it's really not that different. In polar, basically the magnitude, and remember that's a thing that has to be positive, increases by C. By A, C. Yeah, C times vector A. Now that's sort of a loaded sentence that could be wrong in some cases, right? The magnitude increases by C. Well, what if C is 0.5? Okay, then it decreases. I mean, we mean it's multiplied by C. It's increased by a factor of C, and if C is 0.5, then it gets smaller. But what if it's negative? If C is negative, then it flips direction. That's hard to describe mathematically, right? You're used to this Cartesian system where this is positive, this is negative, but in polar system, it's all about the angle. Okay? This is actually evidence for the malevolence of God. Okay? We'll talk about that more when we get to electrostatics, but it really is. So what you'd say, one way to think of it mathematically is that the magnitude becomes C times the magnitude A, and the direction is the same if C is positive. And then if it's negative, you could say the magnitude, it has to be the magnitude of C times the magnitude of A. Right? Because if C is negative, this product has to be positive because it's a magnitude. And then you could say the direction is 180 degrees. You flip it 180 degrees. Okay? These are not mathematical moves you're going to do. You will not see this written in a textbook anywhere. I'm just trying to give you an idea of what it means to multiply by a scalar. This is just an awkward mathematical way of saying this. Right? See the connection? See how they're the same thing? Magnitude changes. If it's negative, it flips. If it's not negative, it stays the same way. That's all that is. To do this properly, real mathematically, we have to get out the theta hat unit vector. So you don't want to do that. Okay? It changes direction. That's also the malevolence of God. Okay, so polar. Now Cartesian, this is why we love Cartesian. This is very easy. So if A is AXI hat plus AYJ hat, and I'm already getting texts about how stupid unit vectors are. I know. It's okay. Then if we multiply by C, then it's just C AXI hat plus C AYJ hat. That's it. You just multiply each component by C. If C is negative, it makes the component negative. If C is positive, it keeps the same sign, whatever it was. Okay? And it works positive or negative, right? So in this case, if A here looks like it's, oh, well, no, that's more complicated. Yeah, if A here is 2, if C is 2, then to go from here to here, you just multiply each one of these by 2. These are already negative, apparently, because they're pointing down. So you'd have 2 negatives here and then the positives here. If C here was negative 0.5, and these two were negative, making it point down, the negative constant would make them both positive, and it'd point up. And it'd be a little bit shorter because they're 0.5, and this would happen. Okay? So this is like what you will really actually do. You may not notice that you're doing it, right? But there is an equation called F equals ma. Right? So if you're doing that really as a vector, you're taking the acceleration vector times the scalar mass to get the force vector. So it does happen. Right? You will actually do it, even if you don't know it. Okay. Let's see. So now, we multiply a scalar times a vector, and then the other thing we got to get good at is, of course, adding vectors. So let's do that in polar and Cartesian real quick, and then we'll actually get to physics before the day's over here. So let's add two vectors, A plus B, right? Let me get this out of the way. Add two vectors, A plus B. Let's see. So now we're going to do it in both ways. We're going to do it as a diagram and polar. I'm just going to make them the same thing, because that's really what polar is, right? It's the way we do this diagrammatically. I'll get to this question in a minute. So there, it's the famous thing you've heard of, head to tail, right? So if we have A looks like that, and B looks like that, you got to remember you can move vectors around if you want to. We'll talk about when you can and when you can't when we actually get to physics. But for now, you can just slide them around. So if you want to add A plus B in diagram or polar mode, you add them head to tail. And this is why we did that anatomy lesson at the beginning. So you'll know which part is the head and which part is the tail. The arrowhead and the tail is where the feathers are. So you draw A like that, and then you draw B like that. So I just moved this over here, and then the sum, therefore, is here. A plus B. So you add them head to tail, and you go from the tail of the first one to the head of the second one. And it's just sort of visually what you would expect. Right? So you could ask yourself, does it commute? Does A plus B equal B plus A? You could ask yourself that. So let's see, for that you would say, well, what is B here? And I want to add A to it. I'll just slide it over here. All right? And what is B plus A if I cheat a little bit? Same thing. Right? The order we added them didn't matter. It came out the same. Right? So that's how you add vectors, head to tail, etc. That's doing it diagrammatically. If you tried to do it polar with math, it's just ugly. We don't bother. You got to use the law of cosines and unit vectors and polar. It's a waste of time. So don't bother. Let's do it Cartesian now. So we care about diagrams. We care about doing a Cartesian. Here's another reason we like unit vectors in Cartesian. AX plus BX I hat. You just add the x components. J hat. That's it. You don't have to do any drawing. You just add numbers. This is why we like to do problems in Cartesian. It's much easier than turning it into a geometry problem. Now, let's do one real quick here. So we'll actually give ourselves two actual vectors. A equals 3 I hat plus 3 j hat. Make sure you know how to use those. 3 I hat plus 3 j hat. And B equals negative 2 I hat minus 5 j hat. Ooh, minus 5 j hat. I'm going to give myself more room to draw it over here. Oh, good. Let's see. So you can make yourself a nice big Cartesian coordinate system that goes 1, 2, 3, 4, 5, 1, 2, 3, 4, shoot, 1, 2, 3, 4, 5, like that. So head to tail, right? So, I'm sorry, not head to tail. Well, let's just draw them first. Let's draw A and B. So 3 and 3. So A is 3 I hat, 1, 2, 3, 3 j hat, 1, 2, 3. It's about there. So it's at 45 degrees, basically. So there's A. And B was, negative 2, negative 5. 1, 2, minus 2, down 1, 2, 3, 4, 5, so about there. So there's B. Okay? So now let's do it Cartesian first. Right, if we want to do it Cartesian, we just say, well, then a plus b is what? 3 minus 2 is 1 I hat. Right, there's 1 I hat, and 3 minus 5 minus 2 j hat. So we don't even have to draw anything. Right, we just draw 1 minus 2. Like that. Right, there's a plus b. And we're done. But we could say, let's check it. Let's see if it's right. So let's pick this up and move it head to tail with a. Oh, look what's going to happen. How beautiful. Look at that. There's b to there. And it comes right down to the exact same place. You can do it either way. Right, a plus b. So that's literally how you do it in both systems. And now maybe unit vectors make a little more sense. Maybe you love them a little more. You did this. Maybe these people that have done physics for 400 years know what they're talking about. Possibly. So here is I hat at a unit of 1. Here is j hat at a unit of 1. And I say, I want to describe the vector 3i hat plus 3j hat. It's really vector addition. 3i hat is there. I took the I hat, I multiplied by the scalar 3. 3i hat. Here, 3j hat is here. I took the j hat vector, I multiplied it by the scalar 3. And then I just vector added them. This vector added head to tail with 3j hat. Boom. Right? That's what the unit vectors are. They are real vectors. Just because they have a little caret hat doesn't mean they're not real vectors. They're real vectors, the magnitude's 1, and that's how we use them. Okay? Okay. Finally, we're done with vectors. Somebody asked if you can multiply vectors. Yes, you can. Do you all want to go through vector multiplication right now? No, you don't. No, you don't. So no, you can. There's two ways. There's dot product and cross product, and we'll use a little. We might do both. I forget how deep we go mathematically. But yes, you can multiply them. But for kinematics and forces right now, we don't need to multiply them. Okay? Okay, so now, let's see. That was all we're going to talk about on vectors, right? That was your long introduction to vectors. We did notation and components. We added, subtracted, multiplied by a constant. Now we got to actually start using them in all of this. Right? Now we got to use them in kinematics. All right. Here we go. Kinematics. Oh. No wonder I'm not getting many questions. I have to write my number. Okay. So what we're describing in kinematics is 2D motion. Motion. Okay. So keeping up with x and y. That's really all it is. My transitions are so effective. Everybody feels like, okay, we got to reset. We got to reset. We're done with vectors. So that's all it is. It's doing the exact same thing you did before. X equals xi plus vit plus 1f at squared. Now we also have y equals yi plus vyt plus 1/2 yat squared, whatever. Okay, it's the same kinematics. We just got to do it both ways. All right, that's really all it is. But then how to do that in the math, it gets complicated. So let's start by thinking about a mass on a frictionless surface. Okay. And we're going to say that a vector equals 0. So what does that mean? If a vector equals 0, what is ax? 0. What is ay? 0. So this is uniform motion. Constant or no zero acceleration. Okay? So remember, we just talked about it. Ax equals 0. Ay equals 0. Uniform motion. Okay. So we're going to draw a trajectory. Shouldn't the graph reflect on the opposite side of the y? Did I mess that up? Probably not. Okay, I might have. Let's see. I don't have time to look at it. Let's draw a trajectory now. Okay, new kind of graph. It didn't make it onto that list. But now I'm going to draw a trajectory. And that means this is not a kinematics plot. This is actually what something did in space. X and y. So here x and y means the x-axis and the y-axis in space. Okay, how am I going to represent time on this drawing? I'm not. Okay, if this was like class with the stupid animations, I can make something move, but it's not, okay? It's a regular class with chalk. So I'm going to draw one here, and it's dotted. And you know what dotted means? It used to be there, okay? It's not there anymore. And then I'm going to draw like a line like this, and I'm going to draw it solid there. And that means now it's there, right? It moved from one place to the other, okay? Because I can't make it move. Okay. So what we want to do is describe that motion, okay? Let's see. So let's put some bullets here. So one is, let's think about some vectors. R naught. Can you guess what R naught might be? So R in general is the position vector, okay? It doesn't mean radius when you get into higher level physics. R means position. So R naught means the initial position. So if I had to draw the initial position vector on here, I would have to draw it from the origin. I have no choice. Must start at the origin like that. R naught. Okay? But now I may also want to draw the velocity vector. So let me write that. R naught, initial position. Now, what if I wanted to write it in vector notation? Oh my God. Can you handle this? X naught I hat plus Y naught J hat. Right? You're used to having an initial X and an initial Y. Let's put them with unit vectors and call it a vector. Look at that. So there's X naught, and here's Y naught. So there's that unit vector becoming useful again. Now I meant to draw this dotted. Let me go back with your pen and make that dotted. Let's see. That's the path. So now we want to draw, say, the velocity vector. Okay? So we know it's a constant velocity because we know it's not accelerating. So here, I'll just draw it here where it was. We'll draw it like that. And we know it's along the path like that. So you could draw it there. All right? But you might say, wait a minute, but I could also, okay, so this is like this. V, it's got an X component. It's got a Y component. Maybe you can kind of see that, right? It's got some Vx here and some Vy there. That's a little weird, right? Because here I drew them on the coordinates and here I didn't. And you might also say, you know, I didn't want to put it there. You should have put it here. You're living in the past putting it here. You need to live in the present and put it here. Okay? Well, why can I put it either here or here? When is it that you can move a vector around and when can you not move a vector around? You can almost always move a vector around. Okay? The reason I can move velocity and not position is the position vector is in a coordinate system and we always draw a spatial coordinate system. Right? Almost every problem, you're drawing x, y for a trajectory as the x position and the y position. Therefore, when you draw the position vector r, you really do have to put it at the origin for it to be the real position vector r. When I draw the velocity, this is not a velocity coordinate system. If you wanted to, you could draw a velocity coordinate system, and then you're doing solid state physics. So don't do that. Okay? Don't bother to draw a velocity coordinate system. Just put the velocity vector where it kind of makes sense when you're thinking about the problem. And then if you really want to see the components, draw yourself a little baby coordinate system. Oh, there's Vx and there's Vy. See, I kind of drew a little velocity coordinate system. I can put it anywhere I want. Because the origin of the velocity coordinate system doesn't care about the origin of the spatial coordinate system. They're different coordinate systems. Why would they care? It's like an alternate universe. Okay? So that's why when you do problems, you'll put velocity vectors anywhere. You'll put acceleration vectors anywhere. You'll put force vectors anywhere. But the position vector is the one that you actually have to think about where the origin is. Okay? So we could describe this one this way. We could say, okay, that's moving there. That's moving there. Another thing about 2D motion is that the x and y motion are independent. In this case, motion are, x, y motions, I'll say motions are independent for now. Okay? So some people take this too far, and they think it's a law of the universe that x and y motion is uncoupled and independent. That is not true at all. All the problems you do that make sense, it's independent. Right? When I throw something in the air, x and y are not coupled and independent. Right? It just moves along in x. There's no forces in x. There's one force in y. They're independent. But say circular motion on a string. You know how they just give you the formula for that and they don't derive it? That's because it's coupled and really hard. Okay? So x and y is not always independent, but in this case, we'll tell you when it is. And in this case, it is. It's just something floating on a table. So there's no forces, there's no hill or anything like that. Okay? So the way you would solve this, the way you would work on this problem, if this were a problem, it's just an idea. Let's see. So if you wanted to do it, mess with it, you'd say apply A equals 0 kinematics, right? Uniform motion kinematics. If this were a problem and you were given initial values and you were asked where is it going to be, so let's think how you would do this. Like if you're not fully down with vectors, if you say I don't want to deal with vectors, you'd say I'm just going to do the x and y motion separate because you said they're independent. And you can do that. You can say for A equals 0, how do I describe the position? X equals x initial plus v x t. Well, you're really just using the components we gave you, right? So x naught, I called it naught because I'm old, right? X naught plus vx, that was the component here. And you say, okay, I can't do vectors. I'm just going to call this y. Y equals y naught plus vyt. You can do the whole problem that way. You don't have to write it as a vector if you don't want to. Sometimes, though, a problem's a little easier if you write this. What if we wanted to take everything about the x? We'd put it in here. X naught plus vxt I hat. Look at that. You can put the kinematics in parentheses and just call it I hat. Plus y naught plus vyt j hat. I dare you to do that once. Okay, it means the exact same thing. Okay? All we're saying is the position will follow these coordinates around. So therefore, this is the position vector. Okay. Does anybody feel super bold? If you feel super bold, I dare you to do this. Oh my God, look at that. Who would ever do that? Right, what does that mean? What is it? It's the full vector notation. R, the position vector R, is the original position vector R naught plus Vt. It's mathematically identical to this. Right? It's x naught plus y naught, x naught I hat plus y naught j hat plus vxt I hat plus vyt j hat. And it's just regrouping them from here. See? Same thing. This is how like grown-up physics books would do it. It's not how I do it. Okay? So I would recommend you always want to start here. Think about this. Sometimes this helps. Sometimes. Not always. Okay? So let's see. Now, so that we're not going to do that problem, but another thing to think about is identify vectors in kinematics problems. We sort of did that. We drew r naught, we drew v's. We didn't draw any acceleration vectors yet because acceleration was 0. We'll do it in a minute. One thing we want to do is take these concepts and go back to our graphs. Right? So on the homework, one of the problems says draw the x versus time and y versus time position graphs for this motion. So that's what you got to do. It's multiple choice, right? You don't have to actually draw it, unfortunately. But let's just think about it. I'll get you started, right? I'll get you started. So it looks something like this. Remember, that is x versus y, but now we're talking x versus time and y versus time. Where does it even start? Right? You got to think, where is it going to start and what's the slope going to be? And are the slopes the same? Think about how it's moving. Is it moving faster in the y or faster in the x? I don't know. And does it start, do they both start here? No, they don't start there. That's the origin. Does it start at the origin? No, it doesn't. It starts kind of high on the y, yeah, and kind of low on the x, doesn't it? And then as it evolves, they're going at different speeds, right? So this is a case where you've got to think about a physical actual trajectory on a plane. Think of it as uniform motion along that line and see if you can turn that into kinematics graphs. Or see if you can get, you got a 50% chance, right? There's 4 sets and you get 2 guesses. So. But you're going to do it with your brain, I know. Okay, so this was 2D motion, 0 acceleration. Okay, now we're going to let something accelerate. Okay, now it's going to get exciting. In the 65th minute, it's going to get exciting. It's like a soccer game. Right? Let's see. Except it's going to get exciting. An international soccer game, not the women's soccer here. Those are all exciting. It's the international games where nothing happens. That's what I meant. Okay. So now we're going to do a demo and think about something called shoot and drop. Shoot and drop. And the question in shoot and drop is who hits first? Okay? So this is shoot and drop. You may have seen this before. This is a very popular, common demo that everybody does, right? There's these little thingy-bobs here, and one of them is going to get shot that way. And one of them is on a little rod. It's just going to get dropped. And the question is, which one will hit the ground first? All right? Which one will hit first? Will the motion this way change what happens? Let's think real quick. All right, so here, what am I plotting? I'm plotting y, and this is a trajectory, so I'm plotting x like that. Okay? So this is drop. It's not going to get shot to the side. It's going to start here. And we know from last time it's going to accelerate down at 9.8 meters per second squared from last week. And then shoot will look something like this. All right, here it is. And it's going to be given an initial velocity, v naught. Okay? So in the x direction, it's just going to move forward with that velocity. But in the y direction, it's also going to accelerate down. Because we know it's going down, everything falls at 9.8 meters per second squared. And this is another case where the two motions are not coupled, where they're independent. You treat them independently. So I'll give you a hint. What's going to happen is this one's going to drop. And this one makes a motion like this. Okay? It looks just like the kinematics graph, doesn't it? Like a parabola. But it's actually a trajectory. And the reason it looks the same is the x-axis here and the x in time are both linear. Never mind. Don't worry about that comment. Okay, let's watch it drop. Let's see. How long does it take to get down? Y final equals y initial plus vyt minus 1/2 gt squared. So I put a minus because it's dropping, because g is just a positive, is a constant. Constants aren't negative. So it's negative 9.8 meters per second squared. Okay? So I could put in some numbers and say we want it to get down to 0 and start at h, right? So the final is 0. The initial is h. It's not moving. We drop it from rest, minus 1/2 gt squared. So you could solve that for when does it hit? It hits at the square root of 2h over g. Right, the square root of 2h over g. T square root of 2h over g. Fine. This one's moving in 2D. We've got to solve both. Okay? So for the y, we say y. We say this basically the same thing. It's y final equals y initial plus vyt minus 1/2 gt squared. All right? Okay, so in the y final is 0. The y initial, it started at h. Is it moving in the y? No, we're shooting it this way. So v naught vector is vx I hat plus 0 j hat. Right? It's level. It has no y component. Therefore, this term is 0. See that? Minus 1/2 gt squared. So we solve that for t. What do we get? Square root of 2h over g. Did we even use the x component? No. Right? Because they're separate. So how long it takes to fall is completely independent of how fast it's going this way. We could do the x motion. We could say x final equals x initial plus vxt plus 1/2 at squared. Okay, is it accelerating in x? No. That's 0. Where did it start? It started at 0. I'm sorry. The final position of x is x final. X initial is 0. vxt. So we see in x, it's just d equals vt. Right? So when it drops, it falls just like this one falls, and it just cruises that way. And when you put those together, it makes a parabola. That's all it does. Okay? So let's see if that's true. Let me check these questions real quick. Shouldn't the graphs reflect? Oh, no, that's old. Why is r not a vector, not a scalar, if the position is at the beginning? I understand. Yeah, I'm not sure. And let me just check the last one. Yeah, there's some concern about the initial, that old r naught. We'll get to it some other time. Okay, so here it is. So we're going to see this one's just going to fall, this one's going to shoot. And the only way to test this is by listening. You want to listen for them to hit and see if they hit at the same time. Let's see. I think they hit at the same time. Did anybody hear 2 hits? I only heard 1 hit. Let's do it again, just because it's fun. Okay. And that one's going to get shot, and that one's going to get dropped, and it has to be level. If it's not level, what do we make non-zero? Vy, exactly. Ooh, let's do it non-level. Let's see if they hit at the same time. This is like the counter proof. Oh, they didn't hit at the same time, did they? I've never done that before. That was exciting for me. I enjoyed that. Quick questions, and I'll tell you what people get wrong about this. Why is it negative? Yes, so this is important, okay? Why is it negative 1/2 gt squared? So in the general formula, it's plus 1/2 at squared. But we want to say we know the real, I made y up positive, and we know the magnitude of the gravitational acceleration down is 9.8, and we know it's down. So I manually plugged in minus 9.8 for A. Okay? So I put the minus here, and I put the 9.8 here. Okay? You could, if in your brain, if you're good at this, you could say, no, I'm going to put a positive there because I'm going to remember that G is negative. You could. It's not a good idea to define constants negative, but you could. And then you get to here and you'd say, oh, no, I have a negative sign here. You can't have a square root of a negative. You'd say, oh, no, don't worry about it because I know the value of G is negative. And you're just going to confuse yourself. Okay? So don't ever define a constant negative. The constant is 9.8. The negative is because you know it's going down. Okay? So whenever you do this demo, people say, oh, but wait a minute. What if it was going really fast? Right? If it was going really fast, they would have hit at different times, right? Like, no, they would still hit at the same time. It doesn't matter. It's uncoupled. They say, okay. But what if it's going really fast? Like, what if it's a bullet? I'm like, no, it would hit at the same time. That's like the whole friggin' point of the lecture is it would hit at the same time. They're like, no, but we're not so sure. So we're going to do a bullet, right? So this is what we're going to do. And they're going to hit at the same time approximately here. So let's see. I'm going to drop one and shoot one, and we're going to see if they hit at the same time. And you're just going to say they are because you can't follow it this fast, and your head doesn't turn fast enough. Here we go. 1, 2, 3. Roughly the same time. I didn't quite have, I had the angle a little wrong. Let's see. Roughly the same time, okay? It doesn't matter. And then they say, what if it's going really fast? What if it's going really... Okay. Oh, wait, I need one. Ow. Okay. So it's going really fast. Wait a minute. And then we get level close to the same time. But wait, what was that noise? Dr. Stenson messed up. Everybody listen. Did that follow a normal trajectory? No. Because eventually your model breaks down. This is what we can learn from this, is your model is eventually going to die. What is our model? Our model is that everything just falls at 9.8 meters per second, and when it goes this way, it has no force. But if something's moving fast through the air, it has a force, right? It has a drag force slowing it down. And based on the shape of how it goes through the air, it can have lift, picking it up. So the person I scream at is actually correct. Eventually, they won't hit at the same time because other things outside your model will start to take over. There's even another one. What if we sucked all the air out of the room? What if we're on Mars? Okay? Now let's say we're on the moon, and we do this experiment. And here we are on the moon with some gravity. It's less gravity. The thing will go like this. And you shoot it hard, it'll go like this. You shoot it hard, it'll go like this. You shoot it hard, it'll go like this. Will the model ever break down? Yes. Because the moon is curved, so is the Earth. Right? Eventually, you would go into orbit. Right? So every model will break down eventually. But for all the problems you're going to do, they're independent. Okay?